Hi, I'm going to show you in this video a closed loop buck converter, how we use LTSpice to simulate it in 3 different ways, and what configuration we have to set to speed up the LTSpice simulation. So let's get started. If you search over the internet for a buck converter, usually they discuss the open loop buck converter, but in this video I will share with you how I considered a closed loop system. Usually when you look at closed loop system, they have this form of feedback network or compensation network to be considering the feedback into the PWM generation and make a regulation. I have this buck converter here. The input is 50 volt and the output is different from 0 to 50. The output load is 50 ohm here. And at the same point here, I considered another load, but that load will be engaged and connected to the system at 50 millisecond simulation time. So I consider this switch with this driver. This driver is an ideal MOSFET driver because I want to speed up the simulation time, and that's getting the PWM signal from this comparator and this sawtooth generator. I have chosen the inductor and the capacitor values randomly, so there is no specific calculation for this buck converter because my focus today is about feedback. So as you see here, the feedback network is formed by these two resistors to feedback for me 10% of the real output. So if the output is 50 volt, I will get here 5 volt. Okay, the set point for the system here is implemented using this voltage supply. I have considered a voltage supply here and just a random dummy resistor here, and the set point is this 40 volt. Okay, but later this set point here, it will be considered here but differently by mapping the value. Why I need to map the value? Because this network now considers the values from 0 to 5 only. And I want to get a set point here from 0 to 50 to be user friendly and just understand what he sets. Okay, so here we can set from 0 to 50, but this will be mapped by this voltage source here from 0 to 5. As we see here, the value here is 40, and 40 divided by 10, it will be 4, and 5 minus 4, it will be 1. So if we consider 1 volt here as reference, it will generate 40. Why this happens? Because it depends on the configuration of the PWM system that you have here, the arrangement of the and position of your sawtooth and others. I will share with you different configuration in this video. Now, usually when you try to find a feedback system for a buck converter, they share this network as a feedback system. Very rarely to find a different network from this one, because this one is simple one, and also the LTSpice simulation is fast considering this simple circuit, rather than just choosing to do it by multiple operation amplifiers, for example PID control or others. They consider this one just to speed up. Okay, so if you done the simulation using this network now, just to remember that this operation amplifier here is fed by 18 volt supply, but this operation amplifier here is fed by 18 volt and minus 18 volt. Many learners may forget to supply it by negative voltage as well, because the feedback here might be the error might be positive or negative. Okay, that's everything for this network now, and if you want to run it, I want to share with you my control panel spice configuration. This is one of the configuration. Okay, a trapezoidal and normal. You can make it modified and alternative. It will be similar. Why? Because the simulation here is basic. Okay, let's now see the result. The result is this. I have this green line here. The green line is the set point, and the blue line here is the response. And as you see here, the response is stable. There is some oscillation here because I didn't really make a lot of effort to choose these values according to some calculation, but you can play with that and choose them. Okay, back to the signal here. and I prefer to do it vertically. Okay, so we have some oscillation here, and at time of 50 milliseconds here, okay, we engage the second 50 ohm load. So instead of getting, for example, 40 divided by 50, it's about 0.8 ampere. We are getting now 1.6 ampere, for example. Okay, so this is the response of the signal when we change the load. Okay, so you can estimate the response time from this point, 50 milliseconds, for example, to, for example, at the end it will be like 30 milliseconds, which is long time. Okay, you can consider different values from here just to make it faster. I have on the right here some values for initial values. You can ignore them if you want. Okay, the speed of the simulation here is relatively fast. I can now share it with you. So here's the speed. It's not really slow, it's acceptable, okay, but not very fast. I will share with you some tips in the other simulations just to consider the some details and ignore some details in the circuit that might really speed up or slow down the simulation time. So now this is the first network here, and if you looked at the internet, what is this circuit called? It's called there are three controllers, maybe popular controllers. They are called type 1 compensator, type 2 compensator, and type 3 compensator. Okay, so this one is type 2 compensator. You can look at the internet and see what type 1, type 2, type 3 consider for buck converter, and see how they select the values to enhance the response. Okay, so let's now jump to a different feedback system. In this one, I just made some few changes, very small changes. Okay, the first one is I want to implement PI control. Okay, and PI control, this is one format of the PI controller. Okay, and just to isolate this network from my PI controller, okay, I have to consider here a buffer. Okay, so that's why the feedback point here coming out from this point here going to a buffer, and that buffer will consider or implement the isolation, and then we will bring here another version of the feedback to be injected to this PI controller. So this is a PI controller here, and we have similar components, similar everything here, and for the output we have approximately similar response. Okay, why try to feedback this, okay, connected directly to this point here without the buffer, you will have different response. Okay, why? Because this network now will be considered in parallel or series with R5, and maybe it depends on how you calculate the equivalent resistance. Okay, so the input network here will be a mix between these two and this one. Okay, but by isolation I make a different story. I isolate the feedback value from being as a value for the network itself. Okay, so that's the only thing here. Okay, I have chosen because some students, they just ask about how we implement PI control. You have to do it by this way. Okay, so the signal here and the speed is still relatively fast because we have just one operation amplifier, and as we see here, we have some oscillation. Okay, you can play with these values to make it more stable or damped. Okay, what we change also, we change here this resistor. It was a capacitor in the first version, but now it's resistor, so you can just implement the PI. Okay, so there is a third version of the buck converter and the feedback system, but using PID controller using operation amplifier, and there we will stuck in simulation time and also some other details that I considered to make it work. Again, if you look at the speed here for the response, for example, I think you are talking about here about 16 to 20 millisecond, and here if we consider after the change here of the load, okay, we suffer here from, so the simulation is not really fast here. It's slower than the first version, okay? But if we looked at the speed here from this point, for example, to this point, we are talking about also 20 millisecond, about a 20 millisecond, okay? So is there any chance to speed it up? Yeah, you can play with these values, or let's talk about now the third version of the feedback. Okay, here is another version of the feedback system. I will zoom just to make it very clear. At the same thing here, the first part here is similar, exactly the same, okay? And also we have the feedback system here, but it's not exactly the same, okay? What I change here, I change how the position of the sawtooth and also the control signal coming after the feedback also, and also I change here the sawtooth starting, okay, or orientation. It was 0 to 5, now from 5 to 0, okay? I consider these changes because I have to consider also the polarity of the signal and feedback coming out from this operation amplifier, okay? Again, this operation amplifier here, okay, it's working as a comparator and it's fed by or supplied by 18 volt, okay? However, all these operation amplifiers are fed by 15 and minus 15. You can consider 18 minus 18 if the operation amplifier is accepting that, okay? Again, back to this, we have the feedback here, okay? And the feedback, I'm doing here a traditional PID controller, okay? Exactly the same as the books and references. We have a feedback here, and the feedback is passing through a buffer, okay? We have also a set point, and that set point is coming also from this operation, this supply, okay? So this supply is, maybe you can consider it as 40 volt like this exactly, but I considered a changing step response, okay? I will show you now how it look like, okay? So at about 8 milliseconds, it would change from 0 to 40 volt, okay? And this set point now is transferred to this operation, so this supply here, as just another equation here, but without 5, okay? And this is a buffer. So this buffer and that buffer just to transfer the value of the set point or the feedback to these points. And this block here is the subtractor. As you remember, in feedback system, we subtract the feedback from the set point here. And after the subtractor here, we have the error signal. So this point here is the error signal. And I pass this error signal to a PID controller. You can consider one of them, okay, or two of them. I think the P controller will not work as alone, okay? So PI controller will work, and PID will damp also the oscillation higher and also will be better, okay? So I considered here the PI controller, and I change a little bit in the gains by trial and error just to make the response acceptable and faster than the first and second version. This doesn't mean that the first circuit and second version is bad. No, I didn't play with them, okay? So just there are examples, okay, how complicated that you can go and still working. And finally, after I get the subtraction here and the PID here, I'm going to a summer, and that summer also get the value from P and IID, sum them together, and also invert the signal because they have been inverted before, okay? And that control signal now is going to the comparator here, okay, to be compared with a sawtooth and generate for me a PWM signal that's going to this ideal MOSFET driver. You can change that by a different or practical one and still working, okay? But this one just to speed up the simulation. There are some tips here to speed up the simulation. The first one is I have chosen here in the control panel SPICE the modified trapezoidal one and alternative method, okay? This is recommended, okay? The second tip to speed up your simulation is you insert some resistances, very tiny resistances to the power supply. So by right click here, you can insert very small resistance here. Right click here, I also inserted very small resistance here. This will make LTSpice solve the circuit very quickly, and also for the capacitor, very tiny capacitor here. Okay, this is one tip. Second tip is I have here in the transient command, okay, you can play with the maximum time step. Some people I found, okay, they consider 1 micro. 1 micro is very tiny, and it can be considered if the simulation is not very complicated. But I considered 100 just to make it acceptable, okay? For this, you have to skip the initial operation point. I will show you if I didn't skip what will happen, okay? So I will untick this now, but please tick it later, all right? Okay, what else? We can also consider some initial values. For example, the output capacitor. You know, the output capacitor is going to be 40, for example, at the end. You can consider initial condition, but because I want to see the transient, okay, that's why I left it, okay. This option here, option fast access, is not to speed up the simulation, but it speeds up the plotting, okay. So after we give the results and finish it, we can they can plot it very fastly, okay. So this one is just to enhance the plotting, so it doesn't really speed up the simulation. Now before I run the simulation, I want to show you the just the response before I run it, because it will take long time, okay. So here is the results, okay. So as you see here, the value of the command here, the set point here was 0, and at 8 milliseconds it considers the value of 40 as set point. So it jumps, this red line here is the set point as a step, okay, and the green line here is the response, the output value. As we see here, the output is 40, exactly as the set point, so there is no steady state error. There is some overshoot here, but the integrator controller return back to the set point as quick as possible. Now, as I mentioned before, we have at 15 milliseconds here, we have a load step from 50 ohm to 25 ohm, because 50 parallel to 50, it will be 25 ohm. That means higher current. See what's happening here at 50 milliamp here, okay. So this is what's happening, okay. The voltage dropped a little bit and reversed back, reversing to the original value, okay. There are some like rebel here, okay, but this one is not really concerning, okay. That's because of the simulation. But look at the speed of recovering, okay. So if we consider what's the speed of the recovery here from 15 to the point it returns back, I think it will be between 1 to 1.5 millisecond, okay. 1 millisecond recovery time or settling time is very good, okay, compared with 20 to 30 millisecond in the first and second and first version, okay. So this is one example. However, there is some overshoot here. I think if you played with these values, I think that you will get better results, okay. Now, as I mentioned before, we have unticked this option, and I have seen some people they stuck with the simulation, because when we run it now, I will run it now. Run. Look what's happening at this corner here, okay. It says stepping, okay, and still now stepping source, and it achieves 100%. So it finished the 100%, but it says here press escape to quit. So what you have to do now, if you have got this message here, just escape once, and once you escape the first time, it jumps to another run for another stepping, and now it reached 100%, okay. Sometimes it takes longer time than what you see here, but we have now another 100%, and it says here escape to quit. So don't escape until you get 100%. I skip another time, and it says here pseudo transient analysis, and it tries now to find a solution, but also press escape to quit, and I press escape 3 times now. Once I press the 3rd time, it starts simulating. So how many times I press escape? It's 3 times. Okay, once I see here 100%, I escape. Another 100%, I escape. Another PC do simulation, I escape. Okay, however, you don't need all that if you check the option that I showed previously. So the simulation now is considered slow, not really fast, okay, but acceptable. Okay, so I will stop now the simulation and go to this again. And if you skip the initial operating point solution, and now I will run it, all the messages that will stop the simulation here and ask me to escape will disappear. Okay, and the simulation will start straight away. So here's the simulation. Okay, and it goes now at the start quite fast. Okay, but later it will jump to 40, asking for step response. Okay, so this is the step, and this is the green is the response. Okay, and it will be similar to the one that I showed to you previously. Okay, while it's finishing here, I want just to bring your attention to some points. I have chosen to make it like this because the students sometimes want to understand how we can implement PI controller using the traditional method or traditional format of the PI controller. Also, just to make the signals compatible with the PWM here and the PWM generated here, I have made some changes, and these changes you have to understand and try to understand the level of signal here and how we compare it. Okay, and after some understanding, I have chosen the sawtooth to start from 5 to 0, not from 0 to 5, and also to make it on the inverting part here, and the control signal to the non-inverting input here. Okay, by this way I have been successful to get the output as you see here. Okay, so there is some overshoot. I consider it as a high overshoot, but you can play with the signals here, or sorry, with the values. Okay, and finally here at 15 millisecond, it will consider another step. You can also play with this value here. Okay, this is the step response here. Okay, play with these to make it different step response, maybe 2 step responses from 0 to 20 and from 20 to 40, for example, and see how it's going from one point to another. Okay, or maybe you can down it from 40 to 20 and see how the response also going. So I'm testing here a loaded change and also a set point change at the same time, and see how the response is going. And maybe if we consider the response time here from this point, which is 8 milliseconds, to where it starts approaching the steady state value, approximately this point here. So it will be from 8 milliseconds to 11 milliseconds. Okay, or 12 milliseconds. It will be 3 to 4 millisecond settling time. 3 to 4 milliseconds is very acceptable. Okay, and you have to, sometimes the responses are different because the initial conditions are different. So that's why I have selected this time, or chosen to start it after a few times of the 0 point, just to make at this point here, or at this period here, to make the system stable and reach the steady state. Okay, and finally I got another step just to initiate the system, and it's already having some values for the charge of these capacitors, and also maybe the inductors and other things. Okay, that's everything for the simulation of the feedback system for a buck converter, and I hope you have found it informative and also as acceptable example of using LTSpice to do this simulation. If you have any comment, if you have any correction that I made, there are some mistakes, for example, or if you have some recommended documents to do that as well, or other examples, please just mention it, and we will consider it also in the future. Thank you very much.